So this is our BYU Electrical and Computer Engineering Junior Project. It's basically a way for juniors in order to be able to apply the things that they've learned in their junior classes in a project similar to what seniors would do as part of their senior project. So for us, the junior project consists of building a fully functional laser tag system that drew upon our coursework from both signals and systems, as well as embedded programming and analog design. So the system really consists of three main parts. We have a transmitter board, a receiver board, and then this is kind of the brains of everything. This is the Zybo board where we did our embedded programming.
So the specifications for our project are to have 10 player frequencies so that 10 different teams with these same components can be playing at once, to have a 40-foot range of hit detection. It needs to be able to be played outside and inside, so that requires us to filter noise from the sun, from fluorescent lights, and other noise sources. And also we need to have low power consumption, as we're running from a 9-volt battery and a USB rechargeable battery. In our analog design course, the first thing we did was build the transmitter. The transmitter controls the trigger of the gun. It controls the hit LED, which indicates when you've been hit, and it controls the shooter LED, which uses a BJT stage to drive it with 20 milliamps. The second thing we built in our analog course was the receiver board. The receiver board takes a signal from the gun, from the photodetector, and amplifies it to a signal that the Zybo board can understand. The signal coming in at 40 feet is at 20 nanoamps and needs to be amped up to 100 millivolts peak to peak, which is a 5 million volts to 1 amp gain. The receiver uses these BJT stages to do the amplification, and also capacitors to limit the frequencies that are out of range of 10 kilohertz. It is a second order low pass filter. At the end of the receiver board, we have a diode that voltage limits it to 700 millivolts.
So the Zybo board was the final element of the project. The embedded programming that we did involves 4 state machines, one that controls the LED letting you know if you're hit, another one that that does the transmitting on your designated player frequency number, another one to control lockout mode. In other words, when you get a hit or when you have shot, there's a period of time in which you cannot receive additional hits. And then the trigger, which also limits you to 1 shot per 200 milliseconds. So we, as well as the state machines, we also implemented the filtering. Like was mentioned before, we wanted to be able to filter out some of the frequencies that are emitted from the fluorescent lights. So that again was handled in the filtering stages. We had implemented one low-pass FIR filter. It was of order about 100, and it also took care of the decimating because we were sampling around 100 kilosamples per second. And then we also implemented 10 IIR filters, each of order 11, and those were for each one of the player channels, or the frequencies which those players are firing on. As well as the filtering, we also implemented a detection algorithm in which to determine which players scored hits on you. All of this basically utilized the ISR for sampling the ADC values coming off of the receiver. This is our improved system. One of the things you'll notice is that we don't have to be tethered, obviously, to a computer or anything to run the code. And so in order to do that, we created a boot image which allows the board to boot directly from an SD card, which we have a slot for right here. So in other words, using the Xilinx SDK, if I can get this to pop up, we created an image that we just put on micro SD card. We can then load it into the board, snap that back down, and now by switching the jumper pin, it will boot from the card, and we can then run our system wire-free.
After loading our code onto the board and connecting everything, we decided to make some improvements. One of the things we did was create a rumble pack for our gun. This was done by getting a small motor from a cell phone vibrator and putting it into the handle of the gun. This allowed us to, whenever we get hit, to have a tactile indication that we were hit by vibrating the motor inside of the gun. This also created some auditory noise as well, so that you could hear that you were hit. Another modification we made to our system was printing the receiver board onto a PCB. We designed it in Eagle, and we sent it to our shop on campus, and we were able to print it out and be able to put the components on the board itself. That made it so that the board was a much smaller footprint, and doing that reduces the noise because the components are closer together, as well as having a more secure connection.
So some of the issues that we encountered while designing it was probably number one, the design of the gun, which we were not involved in designing the gun, but the signal from the photodetector comes through this coax, and unfortunately when the gun was designed, the signal was placed on the shield of the coax, which means that it's very easy to get noise on this signal, especially when you have these other wires close to it. So if we could have redone it, we would have probably rewired this so that signal was protected on that. Obviously, another kind of byproduct of this problem was the fact that because we're using a rumble pack and it's a brushless motor, it does create electrical noise, and so that's something that we did notice, is that we do get more noise in our system when we're using the rumble pack. Now, we also probably could have improved that as well by using a coax on the motor rather than this two-wire setup. But thankfully, our filtering is robust enough that it pretty much handles the noise okay. But again, with more time, we probably would have made a wiring improvement there.
Because of the frequencies that we chose, and because we had 10 frequencies, we had some harmonics in our system. The channel 0 is frequency 1.1 kilohertz, and channel 7 is 3.3 kilohertz. This causes issues whenever a player on one of those channels fires at us, because our system will detect the harmonic every once in a while. Another issue that we faced was the self-detection problem. Because the photo detector and the shooter LED are close together in the gun, it picks up itself whenever you shoot sometimes. To show you the response of our FIR and IIR filters, there is a test that's been written that can show us the response from our system. This is the FIR response. You can see that the red is out of range and it's falling off quickly. This is the IIR response of each channel, showing the power going through each of the channels at one time. You can see there are side lobes and a little bit of noise on other channels, but the difference is by 2 magnitudes. Here our system is in continuous power mode, where the shooter LED is constantly on and the photodetector is constantly detecting. Right now we're currently set as player 0, and so our frequency is shown here. That's because the detector is seeing our shooter LED. You can also see noise on the other channels. There's only a slight bit of noise, and it's insignificant compared to channel 0. You can see on channel 7 and channel 4, which are harmonics of channel 0, that there's also a considerable amount of noise, but still it's out of range using our detection algorithm.
So here we have both guns set up in shooter mode or in player mode. This gun right now you can see is set on channel 2, and this one right here is set on channel 6. So if I If I shoot from channel 6, you'll notice it registers a hit on channel 6. Again, when I pull the trigger, if you'll watch the hit LED, it illuminates. Again, going back this way, I will shoot on on channel 2, and you can hear the vibration go off, and we get a hit on channel 4. Excuse me, I was on channel 4. Shoot again, another hit, another hit. Similarly, go back. You can see it registering on that channel.